Here we've got a pair of sectors of circles. We're told that this smaller sector is mathematically similar to this larger sector. In other words, between the two of them, there's a reduction going on. So we've scaled this down. So we take this picture and scale it down to get this one. And you notice that this length 50 has reduced to this length 30. Now, because it's smaller, 30 is smaller than 50, we get the reduction scale factor by comparing this 30 with this 50 and putting the smaller number on top of the fraction. So 30 over 50, or 3/5, divide top and bottom by 10. It's the same sort of problem if we were in a situation, say, where that was 10 and then we reduced it to 5. You'd notice the reduction would be 1/2. You're halving lengths. 5 over 10 is the scale factor, 1/2. So that's the same here. We're doing 30 compared to 50, 30 over 50, 3/5. So all lengths in this small diagram are 3/5 of the corresponding lengths in the large diagram. So we'd say that the length scale factor reduction is 3/5. So the area scale factor, and remember, areas involve squares of lengths. So if we had, for instance, a reducing from lengths 2 to lengths 1, that's a scale factor for lengths of 1/2. For the areas, we've gone from an area of 4 down to an area of 1. That's a scale factor of 1/4. We're taking 1/2 times 1/2. There's 2 dimensions involved in finding an area, length times breadth, and each of these dimensions is being reduced by 1/2. So we have 1/2 times 1/2. We're squaring the length reduction scale factor. So if the length scale factor reduction is 3/5, to find areas, we know we're doing a length times a breadth. So the area scale factor is 3/5 squared. 3/5 times 3/5, that's 9/25. So this area will be 9/25 of the large area. So area of small sector DEF is 9/25 of the area of the large sector, which we know is 2750. So that's the calculation that we have to do. 9 divided by 25 times 2750. And that gives us 990. And the measurements for area square centimetres. So the smaller sector is 990 compared to the larger one, 2750 square centimetres. This figure being 9/25 of this one, which is the square of the length reduction scale factor. So, moving on to part B. Let's forget about the small circle. This is all concerned with this large sector and the area 2750 square centimetres. Because we're asked to calculate the angle at the centre. And thinking of the whole circle, we're looking at 2750 square centimetres. How does that area compare with the area of the whole circle. So the area of a large circle would be pi r squared. That's pi times the radius, which is 50 squared. So whatever fraction this area is of the whole circle, that would be the same fraction that this angle at the centre is of the whole angle, which is 360 degrees. So angle ACB would be 2,750 compared to the whole circle, that fraction of 360 degrees. Simpler case if you're confused with that, simpler case if we have this angle here 90 degrees, this area is 1/4 of the area of the whole circle. This angle 90 is 1/4 of the whole 360 degree angle. So it's the same thinking there. So 2,750 square centimetres for this sector compared with the whole circle, pi r squared, pi times 50 squared. This fraction of 360 degrees will give us this angle. So that's the calculation that we need to do. So on the top of this, we have, top of this fraction, 2,750 times 360, and that gets divided by the whole of the bottom line, which is pi times 50 squared. Better close the brackets, that's the whole of the bottom line, pi times 50 squared. So let's work that out. It's 126.05 degrees. Now let's round that off to the nearest degree. So angle ACB is approximately 126 degrees to the nearest degree. So just as a reminder, what we've done, this 126 compared to 360 will be the same as 2,750 compared to the whole circle area, pi times 50 squared. So these two fractions are the same. So that's how we achieved the answer of 126 degrees to the nearest degree. That's Mr. Corsi signing out. Hope you enjoyed the video.